Logic gates are the building blocks of a computer processor. So these are the parts that do the math calculations. So first of all, before we start with logic gates, we just need to have a very quick revision of our binary numbers. So if we're counting in normal decimal or denary numbers, 0, 1, 2, 3, in binary, those are 0, 0, 0, 1, 1, 0, 1, 1. So what we're saying is that if we have 0 and 1, and we want 2-digit numbers, or 2 columns, 2-bit numbers actually in this case, there are 4 possible combinations. So that we can get all 4 possible combinations, we do them in order, counting upwards. So these are our 4 basic logic gates. So this one is called a NOT gate. So the rule for a NOT gate is whatever goes in is not what comes out. So if we put a 0 into a NOT gate, then a 1 will come out, because a 1 is not a 0. If we put a 1 into a NOT gate, a 0 will come out, because a 0 is not a 1. This is an AND gate. This time we get a 1 as our output if both input A and input B are 1. This is an OR gate. So to get a 1 as our output this time, input A or input B, or both, have to be 1. This is an XOR gate, an exclusive OR gate. So most of the time it behaves like an OR gate, but this time to get our 1 out, it can be A can be 1 or B can be 1, but not both. So it must be exclusively A or B. When we join gates together, we get their opposite, or their NOT. So we've got our AND gate followed by a NOT gate. So instead of drawing the whole symbols there, we just draw the circle from the NOT gate here. So this is not an AND gate, so we call this a NAND gate. If we did the same thing with an OR gate, so we drew the circle there, it would become a NOR gate, not an OR gate. And that means all of the inputs are the exact opposite of a normal OR gate. These are truth tables. So sometimes we would put true and false in there, sometimes we put ones and zeros in. So for our NOT gate, we've got to start off by looking at our input. We've only got one input, which is input A. So in binary, we start counting as low as we can, which is 0. Then we go to 1. We can't go any higher, so now we can look at the output. So if the input on a NOT gate is 0, the output is not the same as the input. So in binary, the only thing that's not the same as a 0 is a 1. If the input is 1, the output is not 1, so it's 0, which will give us our completed truth table. For an AND gate, we've now got 2 inputs, A and B. So we've now got to fill these in as binary numbers, starting at 0 and going up to 3. So here we would put in 0, 0, 0, 1, 1, 0, 1, 1. Or if we did it in denary, 0, 1, 2, 3. So let's look at our outputs. So as I said before, the output for an AND gate is 1 if A and B are 1. So we'll look at this line. If A and B are 1, we'll get a 1 out. But they're not, so we get a 0. You look at this one, are A and B 1? No, they're not, so it's a 0. Are A and B 1? No, they're not. Are A and B 1? Yes, they are. So now we're going to look at the OR gate, and exactly the same as the others, we've got 2 digits, so we start off with 0, 0, 0, 1, 1, 0, 1, 1. That gives us all the combinations of those inputs. So an OR gate, we will get a 1 out if A or B is 1. So if we look at that, is A or B 1? No. Is A or B 1? Yes, because B is 1. Is A or B 1? Yes, because A is 1. Is A or B 1? Yes, because they're both 1. Remember, for the XOR gate, that's this one, it's slightly different because you will get a 0 out here because it's exclusively A or B. So we just said previously that when we join 2 gates together, so putting the NOT gate afterwards, the AND gate becomes not an AND gate or a NAND gate. So let's look at the truth table for that. We start off as always 0, 1, 2, 3. So possibly the easiest way to think of this is think of it just like that combination, the AND gate and the NOT gate. So is A and B a 1? No, but the NOT gate would turn that no, that 0 into a 1. Is A and B a 1? No, but because of the NOT gate afterwards, we would get a 1. Is A and B 1? No, which would be 0, but because it's not an AND gate, we've got that NOT gate, it's a 1. And is A and B 1? Yes, but that NOT gate turns it into a 0. So our outputs for a NAND gate are 1, 1, 1, 0. Just go back and look at the AND gate. 0, 0, 0, 1. So they're the exact opposites, which is why we say an AND gate and not an AND gate or a NAND gate. When you come to the questions, you need to please make sure that you answer in the yellow boxes. So your name and class there, and then each of your answers in the yellow boxes here. So for example, on these you're going to name the logic gate, so the name should be in capital letters. So we enter AND gate and then press enter, and it will change your score there. So you do that for these first 6 questions. On the next questions, you need to say what the outputs are. So here we've got an AND gate with 0 and 0 going into it. So the output for an AND gate is if A and B are 1, not 0, 1. In which case then we will get a 0 out. So you would get your 1 point there. So that's the same for all of these with the different gates.